welcome back. Today we'll be discussing Chapter 5, Discrete Probability Distributions. So stick around. Okay, on this chapter, we'll be discussing the properties of a probability distribution. We will be talking about how to compute the expected value and the variance of a probability distribution. We're going to talk about how to compute probabilities from binomial and Poisson distributions. And we're going to finish talking about how to use the binomial and the Poisson distributions to solve business problems. So how will you use that in real life? Remember what we discussed in chapter 1, right? You can have discrete variables, which basically that's when your counting process, like how many classes are you taking this semesters? How many friends do you have in college? Or you can have a continuous variable, which is a measurement process, like how many gallons of water does your pool contain? How much do you weigh? Those type of things. So here again, we have the different types of variables. We have the discrete variables, which is what we are going to be talking today in chapter 5. And then we'll have the continuous variable, those measuring process. We'll discuss that on chapter 6. Okay, discrete variables, right? We know they can only assume a countable number of values. So, for example, let's say you do have a dice and you roll the dice 2 times, right? How many of those times you can get number 4? So the possibilities will be 0, right? You roll it twice and you get different numbers but 4. Or you can get it 1 time or even 2 times. So your possibilities in this case will be 3 times. You have 3 different possible outcomes once you roll the dice twice. If you toss a coin 5 times, then the x will be the number of times that you get heads, and that could be any value between 0 and 5. Now remember, these are exclusible, right? Because you either get 0 times, but if you get it 0 times, you're not going to be able to get it 1 time or 2 times. So getting one value will exclude the others. Probability distribution for discrete variable is mutually exclusive for that reason, because if you get one value, you cannot get the other. On this case, on this example, we're talking about the interruptions per day in computer network, and the probability of getting those particular values is given to us on the right. So again, if you get 0 interruptions per day, you can now get 1 or 2 or 3, so it will be mutually exclusive. This is just putting those values into a graph that you can see. As you guys see, the 0 probability, the probability of getting 0 disruption is 0.35, and so on and so forth. So how do you get the mean? How do you get the expected value of a discrete variable? And what you have to do is you have to do the weighted average. Now, this formula here can look very powerful, look very potent, but it's not. What you need to remember is that the expected value of a discrete variable is the population mean of the probability distribution. And to calculate this value, all you have to do is multiply each possible outcome by its probability. Very simple. So you have the probability of 0 disruption is 0.35. You multiply those and you will get 0. The probability that you will get 1 disruption per day is 0.25. And then what you do is you add all of those probabilities, and that will give you your mean. So in this case, our mean will be 1.40 after you add all of these values. So how do you get the variance? Remember how we talk about those central tendency, variance, standard deviations. How will you get the variance of a discrete variable? Again, here is the formula, which it might look like very impressive once again, but I assure you it's not. So we're going to need to talk about it. And then we already know, right, that the standard deviation is nothing more than the square root of the variance. So once we find our variance, all we have to do is get the square root. Now, again, the formula there to the right, it looks like it's a very powerful and difficult formula, but it's just the square root of the variance. Okay, so here's the example. Look at the formula up there. Again, it looks like it's a very long and difficult formula. So let's just break it down. What you do is you subtract 1 minus our mean, which we already know, we found that already earlier, is 1.4. You square that number, and then you get 1.96. Once you get that 1.96, all you have to do is multiply the 1.96 times the probability of that event happening. In this case, is 0.35. And once you do the multiplication, you get 0.686. You do all of those, and that's how you will get your variance. In this case, our variance will be 2.04. And then you do the square root of 2.04, and that gives us 1.4283, and that will be our standard deviation. Again, remember, it looks like it's a very difficult formula, but once you know what steps to take, it's not that difficult. Again, here are probability distribution, right? It could be discrete or continuous, which we'll discuss on next chapter. But for discrete, what we're talking about today, you can have binomial or Poisson. So the binomial is a type of distribution that have two possible outcomes, right? That's where we get the B, like bicycle. It has two wheels. That's why it's called bicycle, right? So same thing, binomial, it has two possible outcomes. Like, for example, where you are tossing a coin, you could have heads or tails. When you are taking a class, you can either pass or fail. So those are the binomial. You can have two possible choices. So here is an example, right, of a binomial probability distribution. You have a fixed number of observations, n. Remember, when we talk about the letter n, we're talking about a sample distribution, right? So this is a sample distribution. It's not a population distribution. So you toss 15 toss of a coin. You can have 10 light bulbs taken from a warehouse, and so on and so forth. Basically, each observation is classified into one of two mutually exclusive and collectively accepted categories. So heads or tails, right? So both of them are exclusive because you can either get heads or tails. You cannot get both at the same time, but they are collectively exhausted. So between both of them, you have all the possibilities that you can get. Let's say you are measuring how many defective items you are getting out of a production line. So you can either have defective or non-defective. And both of them will be mutually exclusive because it is either defective or it is not. But they are collectively exhaustive because those are your only two options. So remember, on a binomial, you're only getting two options, right? That's where we get the word B, like bicycle. The probability of being classified as the event of interest, which in this case is P with the letter Greek P, is constant from observation to observation. So again, what we're keeping here is the probability is constant, right? So the probability is getting a tail is the same time each time we toss a coin. So you toss the coin, right, and you get heads. You toss it again. The probability that you're going to get tails will be exactly the same as on the first time. It's not going to change. So since two categories are mutually exclusive and collectively exhaustive, then the probability of the event of interest P, the probability of the event of interest not occurring is 1 minus P. So if P is 0.5, the probability of not occurring is going to be 1 minus 0.5, which is exactly the case of getting a heads or tails. The value of any observation is independent of the value of any other observation. So just because you get heads this time, that does not mean you're going to get heads next time. So remember that next time you go to the casino and you're playing the roulette and you're looking, oh, is it going to be black or red? Just because it's been black 20 times, there is no guarantee that the next one is going to be red. The possibility of the next one being black is just the same as it was on the prior one. So some of the possible applications for using binomial distribution will be manufacturing plant labels items as either defective or acceptable. So you either get them acceptable or defectable. It's going to be either or, and between both of them, you will have all of the possible options, right? A firm bidding for contracts would either get a contract or not. A marketing research firm receive a survey responses of yes, I will buy, or no, I will not buy. New job applicants either accept the job offer or they rejected it. So those are some of the applications for binomial distribution. Remember those counting techniques that we talked on chapter 4? So they become very handy here. And so imagine that you have an event that you want to figure out how many heads you get from tossing a coin, right? So you are to toss the coin 3 times. In how many ways you can get 2 heads? So how many ways can you possibly get 2 heads, right? So you can get heads, heads, tail. You can get heads, tail, heads, or you can get tails, head, head. In this case, we do have 3 different ways where you can get those 2 heads, right? This situation, is very simple. We only have 2 options. We're only rolling or flip the coin 3 times, right? So it's fairly simple, but in real life, you're gonna get it's going to get more complicated. So what do you do when things get more complicated, right? And so remember the counting technique that we learned, and this is where it becomes handy, right? So the numbers of combinations uh, of selecting x objects out of n object is, and here is our formula. So you have the possibility of being n factorial divided by x factorial times n minus x factorial. Okay, one thing you need to keep in mind here is 0 factorial is going to always equal 1 because at the end you're always multiplying by 1. So anytime you multiply anything by 0 gives you 0, but at the end you always get that 1. Just remember that, what we learned from prior chapter. So let's get back to the possibilities, right, using the counting technique. So I don't know if you guys like ice cream, but I like ice cream. One of my favorite places to go is Baskin Robbins, which used to be called 31 flavors. The reason it was called 31 flavors is because that's how many flavors you have. So if you go there and you want to get ice cream and you say, I want 3 scoops, and they say, well, you can have 3 scoops, but you cannot repeat the flavor. So you have to pick 3 different flavors. How many possible flavors how many possible combinations can you get? And so if you're getting 3 scoops and your total choices is 31 because there are 31 flavors, and then you have to pick 3 of those flavors, the possibility, the combination of all possible options that you can have, it will be a 31 factorial divided by 3 factorial times 31 minus 3 factorial. So when you do all that equation, you get 4,495. So think about this when you go to Baskin Robbins and you have to think about how many possible options you have from picking ice cream out there. That's pretty impressive. I just want ice cream. Okay, here is the formula for binomial distribution. And on this case here, we do have that the probability that x equals x event of interest given n, and p will be that's what that means, right? The p, x equals x given n and p. Again, n, it will be the numbers of observations, and p is the expected value. All right, here is an example. What is the probability of one success in 5 observations if the probability of an event of interest is 0.1? So basically, in this case, it's telling us our p is 0.1, our numbers of observation is 5, and our x is 1. So once we do the n factorial divided by the x factorial times n minus x factorial, we can get the formula. After you do all of that, we can get 0.32805. So suppose the probability of an invoice payment being late is 0.10. What is the probability of one late invoice payment in a group of 4 invoices? So you have 4 invoices sitting in front of you. One of them, you know that the probability of one invoice being late is 0.10. What is the chances that out of those 4 invoices, you're going to have one that is late? And so once again, once we do the formula here, we get that the possibility is 0.2916. Because this is very difficult, is very tedious work, and to do it by calculator is very difficult. We're going to be using Excel, Jump, and Minitab to do binomial calculation, so we will have a separate tutorial on how to do that in Excel. Discrete histogram will help you visualize binomial distributions. So whenever p equals 0.5, you're going to see that the binomial distribution is symmetrical, regardless of how small or how large the numbers of observation is. Now, when p does not equal 0.5, both p and n affect the skewness of the distribution. So if p is 0.5, it doesn't matter how many observations you have, is going to be symmetrical. But if p does not equal 0.5, then both p and n will decide the shape of the binomial distribution. So here how do you find the mean of the binomial distribution? And here we have our formula, basically is n times p. And how do you find the variance and the standard deviations? So our variance is going to, we have the formula there, and we already know that a standard deviation is the square root of the variance. All right, here is an example, right? You have your mu, you have your numbers of observation, which is 5, your p is 0.1, so you have 0.5. And you have, here we have the standard deviation, and is 0.6708. Once you multiply 5 times 0.1 times 1 minus 0.1, and you get the square root of that, you get 6.08. To get your variance, all you gotta do is you elevate 0.608 to the second power, and that will give you your variance. Basically, what is a Poisson distribution? Basically, a Poisson distribution is a tool that will help you predict the probabilities of certain events happening when you know how often the event has occurred. So you really know how events have occurred, and based on that, you can predict what is going to happen in the future. So basically, give us the probability of a given number of events happening in a fixed interval of time. So you can use the Poisson distribution when you are interested in the numbers of time an event occurs in a given area of opportunity. What we mean by an area of opportunity basically is a continuous unit of interval time, volume, or such area in which more than one occurring on an event can occur. For example, the numbers of customers that is going to show up at the register, the number of people that is going to show up at the counter to order food if you're in a restaurant, the number of computer crashes in a day, the numbers of mosquito bites on a person. The Poisson distribution is useful, and you should use it when you are interested in counting the numbers of time a particular event occurred in a given area of opportunity. So when we talk about an area of opportunity, we're talking about time, length, surface area, and so forth. The probability that an event occurs in a given area of opportunity is the same for all areas of opportunity. So this is something you need to keep in mind. All of area of opportunities has to have the same chance of happening. The numbers of events that occur in one area of opportunity is independent of the numbers of events that occur in another area of opportunity. And the probability that two or more events will occur in an area of opportunity, it should be getting close to 0 once that area becomes smaller. And then we have that the average numbers of events per unit is going to be lambda. Okay, here is the formula for the Poisson distribution. We have the number E equals to negative lambda, and then we have lambda to the x power, and then you have x factorial. On this case, right, E is the Basel natural logarithm system, right, the 2.71828 that is rounded up. The number continues to infinity, but that's the natural logarithm system. How do you find the mean? Basically, the mean is going to be your lambda, And then again, our variance and standard deviation, we can see here that our variance is going to also equal lambda. So we can say that the variance and the mean are the same. The standard deviation, once again, is just going to be the square root of the variance, which in this case is the square root of lambda, which is the expected numbers of events. All right, let's take a look at this example here. So on this one, we want to figure out the mean number of customers who arrive per minute at a bank during the noon to 1 p.m. hour, and we know that is 3.0. So what is the probability that two customers arrive at a given minute? So think about this. You are a manager at a branch, right? So you're trying to figure out how many employees you should hire to work at specific hours. You know, some hours are busier than others. So if you hire too many people, too many tellers, they're just going to be standing there doing nothing, and you're going to be just paying them for nothing. If you hire too few people, then too much people is going to show up. They're going to have to wait in line. They're not going to be happy, especially if it's their lunchtime and they just need to go do a quick transaction and they get back to work and grab a sandwich and get back to work. So the people is not going to be happy. They might go back somewhere else. So that information can be very useful when you are trying to schedule the number of employees that you need. So in this case, you're trying to figure out what is the chance that more than two persons are going to write per minute between noon and 1 p.m. You know that your lambda or your mean is going to be 3.0. So what is the probability that two customers arrive at any given minute? Remember, going back to the rules that we talk about it. So each minute doesn't matter, it has the same opportunity. It doesn't matter if it's between 12 and 12:01 or between 12:40 and 12:41. So all of those have the same opportunity. Also, as you make those values smaller, that number should approach to zero. So, if you go from the minutes to the seconds and you say, what is the probability that two customers are going to show up 0.01 minute? So now that should be getting to zero because the smaller you make, the less likely are that two people will show up at the exact same time. Okay, using the formula here, we have that the probability of two people showing up between noon and 1 p.m. when your lambda or your mean is 3.0 will be 0.2240 or 22.4%. Again, some of these numbers can be very powerful formulas, difficult to compute. So we are going to have a separate tutorial on how to use this in Excel. Basically, the mean number of customers who arrive per minute at a bank during the noon and 1 p.m. is 3.0. So in this case, they're using Excel to calculate the value. Here is how you will graph a Poisson probability. Really easy. You see your values there. You just put them into the graph. You can see for 0, for example, you have 0.065. For 1, you have 0.3033. So you have all those values. Just put them in there. What we were looking at it on the prior one is right over here, right? The probability of 2 or more customers showing up at any given minute is 0.0758. We have 2. On this case, our lambda is 0.5. And that's how we get the 0.0758. The shape of the Poisson distribution depends on the parameter of lambda. So here you can see when lambda is 0.5, how that looks. And when lambda is 3.0, you also see how that looks. Okay, so once again, on this chapter, we covered the probabilities of properties of probability distribution. We did talk about computing the expected value of variance of a probability distribution, computing probabilities from binomial and Poisson distributions, and finally using the binomial and Poisson distributions to solve business problems. So if you have any questions, please reach out to me, and I can provide you the help and the resources that you need. Alrighty, have a good day.